Okay, so some more example problems of how we work with hydroxide and proton concentrations, pH and pOH. Here's a nice problem. A solution is prepared by adding 2 grams of sodium hydroxide to 2 liters of solution. What is the pH? And of course, when I hear the question, what is the pH, I start thinking acid, and I shouldn't. My key tip is, when God gives you a lemon, make a lemonade. And since in this problem I'm being given a base, I should think in terms of pOH and hydroxide concentration. And yes, what we really have here is 2 grams of a strong base, sodium hydroxide, for 2 liters of solution. And if only this were a molarity, I could easily get the molar concentration of hydroxide and the pOH of the solution. So that's easy enough, because the molar mass of sodium hydroxide is 40 grams sodium hydroxide per 1 mole sodium hydroxide. Mass cancels, and now I truly have a molarity, moles per liter of solution. And it looks like it comes out to 0.0250 molar sodium hydroxide. Now, since sodium hydroxide is a strong base, it completely dissociates. So for every mole per liter of sodium hydroxide, I get a mole per liter of hydroxide. For every 0.0250 moles per liter of sodium hydroxide, I get 0.250 molar hydroxide ion, which is what I need to get a pOH. And the negative log of 0.0250 molar sodium hydroxide is a pOH of 1.602. Now I'll address the question, what is the pH? And since pH plus pOH always equals a constant, 14, then 14 minus pOH gives me a pH of 12.398. A very high pH, but that's expected for a strong base solution of significant concentration. Now, what about the next problem? And this lets us tie in some of the things we learned about dilution in addition to the problem. Because here we take 2.5 grams of nitric acid. So I'm going to be thinking pH, proton concentration, because we're dealing with an acid here, is added to enough water to produce 2 liters of solution. Well, let's do this calculation first and see what the molarity of the solution is. We have 2.50 grams of nitric acid in a volume of 2.00 liters of solution. And since the molar mass of nitric acid is 63.0 grams HNO3 per 1 mole HNO3, I can easily calculate the moles of nitric acid per liter of solution. Comes out to 0.0198 molar nitric acid. So, if I wanted to know the pH of this solution, a strong acid, I'd simply take the negative log of this concentration. But that's not what the problem says. The problem says if 25 milliliters of this solution are diluted by adding 50 milliliters of water, what is the pH of the resulting solution? So before I can get a pH, I have a dilution problem to attend to. And that means, since concentrations are inversely related to volumes during dilution, and since we're going from a volume of 25 milliliters to a volume of 75 milliliters, because after all, adding 50 milliliters of solution or water to 25 milliliters of solution gives me 75 milliliters. So if I'm increasing the volume by threefold, I should decrease the concentration of acid threefold. By the same ratio that the volume increased, I decrease the molarity. So the actual solution I want to know the pH of is a 0.00660 molar nitric acid solution. And of course, since this is a strong acid, all 0.066 moles per liter will dissociate and give me 0.066 moles per liter of protons. And the negative log of 0.00660 molar protons is 2.180 for a pH, which is consistent with even a dilute strong acid solution, 2.180. Now, about the only quick, gentle reminder I should give at this point, because pretty much all these pH and pOH problems for strong acids and bases are similar, is we need to worry in some cases when we have a dibasic strong base. By that I mean barium hydroxide doesn't dissociate in a 1-to-1 ratio to produce hydroxide. There are 2 hydroxide ions in each formula unit, and that means 1 barium hydroxide, when it dissociates in solution, gives you a mole of barium, but it gives you twice as many moles of hydroxide ions. So if I'm worried about pHs and pOHs, I need to worry about that slightly. Because, first of all, if I'm given a base, 0.0300 molar barium hydroxide, I'm not going to think pH, I'm going to think pOH, because it's these hydroxide ions that are in barium hydroxide solution. But since this will completely dissociate and give me twice as many hydroxides as formula units, the actual hydroxide concentration in this solution isn't going to be 0.03, it's going to be 0.0600 molar hydroxide. And so this is the value I'd want to use to calculate my pOH. And that value is 1.22 for a pOH, meaning the pH of this strongly basic solution is, as expected, very high, 12.78, and that's the answer to the problem. So the only little twist here was beware of dibasic bases, because you get twice the concentration of protons as you have of the solute from which those, hydroxides, twice the concentration as the solute from which the hydroxides come. There is no equivalent to this with strong acids. There is a strong acid that's diprotic, sulfuric acid, but of course only the first proton completely dissociates. The second one only incompletely dissociates. So it's not a good analogy. In the strong acid world, pretty much you get 1 proton for each molecule of the acid if it dissociates completely as a strong acid. Not true in the basic world, because strontium hydroxide is also a strong base, and it's dibasic, so you have to worry about it there as well. So just one little key to dealing with strong acids and strong bases and their pHs and pOHs.